Well, sustainability is always now and later. So my talk is a little bit of a misnomer, or the title is. Let me start off with what I want you to take home. And the first thing is that climate change is more than just a greenhouse effect. There is the greenhouse effect, but there's more to it than that, and I'm going to show you some of that. The second thing is that small emission sources matter. A lot of times when we think about climate change, we think about big power plants and big smokestacks, and the solutions are solar power everywhere and nuclear power, and that's true. That's true, but there's more to it than that, again. And the last thing is that there's a broad portfolio of solutions available, and we need to think about when and where and who is affected, as well as just the broad reduced greenhouse gases. So that's my message to you: is think in a little more complicated terms. I'm a scientist. I like to complicate things. I'm going to start with talking about human effects on the Earth's radiation balance. Greenhouse gases, yes, but also particles. And then I'm going to go into a special case: carbon particles, little tiny particles, much smaller than your hair, and the role of very small emission sources. And number two is really what my research group works on, so that's going to be some of my things. And then the last is more of a discussion, and I'd be happy if you participated. How do we balance near-term and long-term goals? Usually when we're thinking about the climate change picture, it's a very long-term picture. What might happen in 2050 or 2100, and we have to start thinking about that now. But we also have goals that occur today and in a few years. And so that's what I mean when I say sustainability now and sustainability later. We have the needs of the present and the needs of the future. So first of all, what are we doing to the Earth's radiation balance? I'm seeing people turning off their phones, and I'm just realizing that I didn't do that to mine. So if my phone goes off, you can shoot me. Okay, this is what I call our fire dilemma. We like it. We love fire. Anyone not like fire here? We like it and we don't like it. So it's warmth, and after a while it became sterilization. That was one of our or processing, one of our first uses. Power, mobility, we love to sit around bonfires, we love to stare at them and feel spiritual, and yet the fires have a lot of hazards: poor air quality, their effluents create health damages, and now we're talking about global change from the emissions. When we think about climate change, usually we think CO2, right? And it's funny because for a long time, engineers really tried to make CO2. That was the goal. You want CO2 to come out of combustion. If you're not putting CO2 out of combustion, you're doing it wrong. So climate change is really a successful engineer's problem. We did it right, and now we're making so much CO2 that it's affecting the atmosphere. But there's incomplete combustion products that occurred before engineers were really good at it, and those also affect not only the environment around us where we can see it, but also climate change. So these, whoops, oh no, that's the one I wasn't supposed to push, okay. All right, climate change. CO2, yes, affects climate change. But CO2 doesn't really cause outdoor air pollution, at least not that we can see. It doesn't bother us. We don't think of it as a big urban problem. It doesn't cause indoor air pollution. Well, yes, it does. We don't want the CO2 to be too high, but there's nobody struggling to see through clouds of CO2 when you're burning inside. These other gases, products of incomplete combustion, carbon monoxide, volatile organic compounds, methane, and particulate matter, which I sometimes abbreviate PM, those are the things that we've struggled to avoid for decades or centuries. And so those first create indoor air pollution. People who burn fuel inside, it happens. It happens in developing countries. It happens here. When people burn, people have less visible effluents, but there's still interior combustion. Okay, so these are emitted into indoors or outdoors, and that's what we think of as our air quality problems. And so we've tended to lump these things into indoor and outdoor air pollution, health problems, visibility problems. We don't like that. Let's clean it up. But we haven't really said, and these are climate changers too. We've tended to separate air quality and climate change into two different things. The stuff you can see, the stuff that bothers you, odors, near-term problems around you. They don't spread out very far. And then the good engineer's problem, CO2, is a climate change problem. But all of those pollutants actually cause climate change. So here is a graph that you'll see many, many times from the Intergovernmental Panel on Climate Change. This is their latest assessment report. And the magnitude of the bars on this side indicates that that's how much a pollutant is contributing to warming. And if it's on this side of the line, it suggests that that is contributing to actually cooling climate. So the biggest one, sure enough, is CO2. That's why you hear about it so much. And there are other greenhouse gases, methane, but carbon monoxide, which could be an indoor air quality problem. That's why we have alarms for it in our homes. Some people intentionally burn indoors, especially in developing countries. So that could be an indoor or outdoor air quality problem. There it is. It's got a little bit of a warming effect. And here's NOx, nitrogen oxide, a little bit of a cooling effect. Here are sulfates that come out of sulfur from coal, something that people work on a lot to reduce sulfur emissions so that we don't have outdoor particulate pollution. And yet when those things escape to the atmosphere, they turn into particles. Particles reflect light, bounce it away, and so less sunlight's coming into the earth, cooling. They change clouds, cooling. And here's black sooty stuff, warming. So out of this one fire, greenhouse gases, a lot of them warming, other kinds of gases, warming and cooling, and particulate matter, mostly cooling, but a little bit of it warming. So everything that comes out of fires is actually having a climate effect, even though most of what we worry about is CO2.
Can I ask?
Yeah.
I don't like PCC because they keep, from when I started this scheme, it was very simple. Now they're building it. Maybe.
I hate when people make things complicated.
Oh, what's that CO that they're showing? Is that the sources, the O3T and CO? What are they trying to show the breakdown?
You mean this?
Yeah.
This, for example, or these little slices? Okay. So this is emissions of carbon monoxide. I'll just take one example, and then maybe we can talk about the other ones later. Emissions of carbon monoxide have an effect on Earth's radiation balance, not because carbon monoxide absorbs a whole lot of light. It doesn't. But it does affect the chemistry of the Earth by increasing the lifetime of methane, so that's CH4, by causing tropospheric ozone, which does absorb energy and dump it into the atmosphere. So these little slices are the different effects that that particular gas has. And the same can be done with NOx. We can go over that later. Anyone else, feel free to jump in if you have questions or don't understand something. Particulate matter doesn't get very far, does it? All right, it's just around the cities, and once you drive away from a city like Chicago, the air gets clear. Well, maybe. Hazes are continental by now. We're emitting enough that you can see the plume of pollution coming off North America. Here we're showing a hazy air off the South Asia, so Indo-Asian haze, thousands of kilometers into the Indian Ocean, Atlantic Ocean, and even reaching other continents. So particulate matter, which used to be an urban air quality problem, no longer is. Here's another picture. This is the coast of Asia, and we pick on Asia a lot because it has a lot of people, but this is actually true of every continent that has significant energy use. And what you can see here just barely, it's a little bit bright. Can you see that? If all the lights were off, you could see it even better. So here's particle emissions coming off the coast of Asia. And why can you see them? Why can you see them? You can see them because they're a different color than the ocean. And if they're a different color than the ocean, it means they're reflecting differently than the ocean does. So that means they're changing the way the Earth reflects light. This plume here is even more dramatic. What's happening here is that particles are coming from the continent and they're taking up water. They're interacting with clouds. So clouds that might not be there or that would look different without those particles being emitted are changed. The emission of particles changes the Earth's reflectivity. And that means that particulate matter has an effect on how much energy gets to the Earth. And it plays a role in the Earth's radiative balance, just as carbon dioxide does. So I'm going to...
Any reason why it's going from west to east?
That's the way the wind blows.
I'm sorry?
That's the way the wind blows. So I'm going to be a little more specific about three different things that come from combustion. Carbon dioxide, which the sun's visible rays come in, and then carbon dioxide helps to trap infrared radiation coming back from the Earth. I assume most people know that, but if you want me to explain it further, I'm happy to do so after the seminar. Sulfate particles, here's what they look like if you look at them under an electron microscope. They're very small. They don't look that way here, but they're, again, bouncing the visible radiation away. So sunlight comes in, bounces right away. So this is not an infrared radiation question. And then soot aerosol, which you're probably all familiar with from looking at fires or playing with candles. Somebody here will admit that they didn't play with fire when they were a child. I won't tell your parents. And what happens with black carbon, soot, is the sunlight comes in, and it's black, so it absorbs radiation. You all know that from walking across a hot asphalt on a hot day or wearing black clothing. Absorbs the radiation, turns it into heat, dumps it in the atmosphere. So we've got one thing that's warming the Earth by absorbing infrared radiation, one thing that's cooling the Earth by bouncing away visible radiation, and one thing that's warming the Earth by absorbing visible radiation, sunlight. Three things.
Sulfate aerosol means what? It cannot be potassium sulfate or sodium sulfate.
It's usually ammonium sulfate. The sulfur dioxide from coal combines with ammonium in the atmosphere. They're not emitted together. But people usually call it colloquially sulfate because it'll be something sulfate based on how much SO2 is emitted. Masood, are you asking a question or are you just waving your finger? Okay. They have very different sources, these three: carbon dioxide, sulfate, and soot. Carbon dioxide in metric tons per year is by far the dominant emission. There's a lot of carbon dioxide and not as much sulfate and even less soot. So maybe we don't have to worry about that little stuff. There's a lot of carbon dioxide. Why is it emitted? Carbon dioxide, again, you can't help it. Fuel has carbon in it. We want to turn it into carbon dioxide. Out the stack it goes so far until people learn how to sequester it. Sulfur in fuels, if it's not captured, again, out the stack and turns into sulfate in the atmosphere. Soot, why does it happen? Bad combustion. You can burn a carbon-based fuel all the way to carbon dioxide and make almost no soot at all. But that doesn't always happen. We'll talk about that in a bit. There's also very different atmospheric lifetimes, and this is important. Carbon dioxide might stay in the atmosphere for 100 years. And so once you put it out, it's out there. And you're stuck with it. That's why people are worried about climate change, because the stuff that we're emitting today is going to be there for our grandchildren and their children. And they didn't ask for that. Sulfate aerosol and soot aerosol will be gone in a few days because they get rained out. You know how much clearer it is after a rain. This is another reason, or a big reason, why people don't talk about them when they talk about climate change. Because if we stop emitting particles right now, in 100 years they're going to be gone. In fact, next week they're going to be gone. So it's not a long-term problem, but it is still happening. Now, here's an interesting thing. How much does 1 kilogram of this stuff in the atmosphere affect the Earth's energy balance? For carbon dioxide, it's about 1 watt per gram in the atmosphere. For sulfate, it's about 200. And for soot, it's about 1,800 watts per gram in the atmosphere. So that's, if you take a gram of soot and put it out in the atmosphere, that's like running a space heater in the atmosphere, just a gram. Why is it so strong? Because it absorbs everything that hits it. It loves radiation. Carbon dioxide will absorb at a few wavelengths, but particles interact with visible radiation very well. So they're going to be gone, and they're not as high in emission, but they're really strong. Something about confidence. We have pretty strong confidence, perhaps in not what will happen to the carbon dioxide, but certainly in what it does when it's in the atmosphere. For the particles, we don't know quite as much. It's harder because they're poorly mixed, so the concentrations are high near sources and low far away from sources, and it's just harder to study the average effects. So if you increase carbon dioxide, you get warming. If you decrease sulfate aerosol, you get warming. Wait a minute, don't we want to decrease sulfate aerosol? Chris, you're saying no. What? Oh dear. Now you're getting complicated. Most of the people in this room would like to see probably fewer emissions that resulted in particles that then caused health damage. So a lot of times in the simple case, chemistry aside, we would like to reduce sulfate particles. And there are solutions, right? Use energy with less carbon. Carbon dioxide's not so easy. You can use fuel with less sulfur. You can put end-of-pipe controls on everything. There are solutions. The ones for carbon dioxide are hard. The ones for the others are maybe not cheap, but not as hard. So we've got a bunch of carbon dioxide in the atmosphere, and we've got a bunch of sulfate particles in the atmosphere. And that means that we've actually emitted a bunch of carbon dioxide, and we should be seeing a lot of warming, except we have this reflective blanket of sulfate particles, which has prevented that warming from taking place, because we keep emitting sulfate particles. Right? They may go away very quickly, but we keep putting them out there every day, all the time. And so some of the warming that we should have seen, we haven't seen yet because we have that protective sulfate up there keeping the sun's energy out. Well, isn't that nice for us? Many people want to remove sulfate aerosols. And so when those are taken away by air quality regulations, and they will be, that's being worked on, that mask is going away. And the CO2 that we put in the atmosphere will still be there because it's going to be there for decades. So even if we stop emitting CO2 right now and stop emitting sulfate right now, we're stuck with the CO2. And as soon as the sulfate goes away, it's going to get hot, even if we do nothing else to emit CO2. There are people who are already concerned that we don't quite understand what's going on with the climate. And this graph is showing different tipping points that could occur with different amounts of warming. On this axis is degrees centigrade. And here's things that could happen. Arctic ice could be gone in the summer. Oh, it is very close to gone in the summer. And then there are different ice sheets that could melt, and then out here you start affecting circulation. We're not here yet, but there's a lot we don't know about models, but this blue line indicates the range of warming, not in 2050, not in 2100, the range of warming people think we have committed to by putting carbon dioxide in the atmosphere. The stuff that's out there today, right now, is perhaps in this range. And when I say perhaps, it's that different models produce different amounts of warming, so we don't quite know. But the range of committed warming bounds some of the tipping points that we're not really sure we want to experience. Here's what we have now, realized warming. This is the warming we've seen. When the sulfates go away and when the ocean comes into equilibrium, this is the warming that people think we will probably see. So all of a sudden, climate change is not, oh, we better do something by 2050 and get our emissions under control. We're faced with a challenge right now. We're already in the boat. It's in the middle of the ocean. We got to figure out what to do. For some products, or for some sources that are emitting a little bit of CO2, I'll talk about these really soon, and a lot of products of incomplete combustion, the greenhouse gas measure is a poor measure of the climate impact. I could show you this figure for a power plant that's emitting sulfate, and it might look like it was net zero in terms of climate impact. But what I'm going to show you is what I'm going to talk about next. And this is a small source whose combustion is so bad it's emitting a little bit of greenhouse gas because it's small, and a lot of products of incomplete combustion, many of which contribute to warming. So if you look at these bars, you don't have to understand the numbers. I'm not going to take the time to explain them, and I'm happy to do that after the seminar. But what I want you to see is how big these bars are compared with these dotted bars. In some cases, these bars are smaller but significant. This bar is bigger than the carbon dioxide bar. There are ways of burning things where the climate impact is not in the CO2. It's all in the products of incomplete combustion. And this 100-year tag that I've put on here is the amount of energy added to the climate system over 100 years. So it doesn't matter that these things go away. It doesn't matter that particles go away or that carbon monoxide only lasts a month. In that short lifetime, it adds as much energy to the climate system as the CO2 from that source over 100 years. So it's like a big bang of energy. And yet, if you look at these sources the way people do when they're doing carbon footprint, is counting that bit. So you could choose this source and say, oh, look, I don't have any carbon footprint, but you're still making a big bang in the climate system. So, lesson one, there's a lot of pollutants affecting climate. It's bigger than just greenhouse gases. Okay, this is where I get to talk about my stuff. There's a lot of kinds of carbon. Many atmospheric chemists split them into two kinds of particles: scattering particles and absorbing particles. And I already showed you this, where the scattering particles were sulfate. There are also carbon particles that scatter light. So the big difference I want you to notice is that there's particles that absorb light and warm, particles that reflect light or scatter it and cool. Most particles cool the climate system. This special one called black carbon warms it. Reduce black carbon, warming comes down. Where does this stuff come from? These are pies for black carbon, and I don't have a legend on the pie for the non-black carbon, the organic carbon. So, chemists hate this term. I'm sorry about it. But we call everything that isn't black organic. But let's just look at the pie here, where a lot of it comes from, a lot of open burning. This is a global picture. So that open burning takes place in South America, Africa, in what we call boreal forests, Canada, Russia. What could we control? If it's a good idea to reduce warming particles, what could we change? There's a big piece of the pie from road transport and non-road transport, tractors and so on. So that's about a quarter of it. Okay, if you think about greenhouse gases, you think transport, power plants, you think about big things in cars, right? If you think about these warming particles, it's actually transport, and this other 25% is wood and other biofuels used in people's homes. Now, I don't want to confuse you here because people think that bioenergy is a good idea. Modern bioenergy, where you take wood and you burn it in modern installations, isn't responsible for these black particles coming out. But what is responsible is poor combustion. If you burn things badly, you can make black carbon. So these are a couple of big sources, and these emissions are difficult to estimate. It's also interesting is what happens as regions develop. So what I've done here is I've made bars that correspond to the fraction of black carbon in different regions that represent the sources. Orange is transport, and blue is solid fuel. And in North America, we've got lots of diesel. Why? We have a big country, and we need to get things from one place to another. As you go down in development, you see the contribution of solid fuel increasing and the contribution of transport decreasing. And that makes sense. When you aren't that well developed and you don't have a lot of money, you eat, your fuel is probably wood or crop waste, and that's where most of your emissions come from. Somewhere in the middle, you might start to develop industry. At first, it's not that clean. Anybody who's traveled in a country that has a lot of heavy industry but not a lot of air quality regulations knows what I'm talking about. And then, what happens? People get rich because of their industry, relatively rich, and they start complaining. I don't want to live in this. Clean it up. That's what we did in the early 1900s and in 1950 and in 1960 and then the Clean Air Act in 1970. Our development path looks a lot like this in the U.S. From solid fuel to industry to transport. Yes?
You show power. It looks like North America has the largest increment on this graph of power. And I would think, China's building always one coal power plant a week. And I don't know what kind. I don't think they have baghouses and stuff on them. So I was wondering, would we see a bigger power carbon black emission out of this?
Okay, there's two answers to your question. One is that we don't have good measurements of power plants in China. However, for the most part, a power plant operating well, even if it doesn't have a baghouse, puts out a lot of particulate matter, but very little of it is black carbon. It's a lot of fly ash. The other answer is that there probably is an equivalent contribution from China, because remember, these are just relative bars. There's probably as much from power. It's just that their industry is quite polluting, and they have a lot of residential solid fuel emissions, and so on a relative basis, that same amount of power looks smaller. Here's a general rule about black carbon emitters. The bigger the emitter is, the more information we have about it. In this country, they even have to report continuous emissions. But the bigger they are, the more money they have, the more it matters if they're efficient, and so their black carbon emissions go down because they can burn better. Carbon monoxide emissions go down. Products of incomplete combustion in general go down because efficiency is important. The more money you have, the more you're able to clean up. And these installations, the big installations, the wealthy installations, are consuming all the fuel, or most of it, most of the fuel. So when we think about fuel consumption, we can point something big, tall stack, large industry, lots of information. Please report to EPA every year. But the small sources, the little ones that don't have a lot of money, and I want to be really careful here that we don't blame poor people for everything. This is just a fact. We don't have information about things that have high emissions because they are associated with a lack of resources. Not only do we not have information from them, but if you, as a scientist, say, I'd like to study this poor combustion, it's not terribly fundable. So you get high emissions from small sources with little information, and for products of incomplete combustion like this, you got most of your emissions coming from things you don't understand. So I happen to be lucky, and people funded me to study it anyway. I had to kind of call it something else, atmospheric chemistry. But I'll give you a couple of examples, just a couple of examples from the things that we've done. This is lab tests. In the global emission models, you want to make a model of particles, go into the lab and burn some wood and say, here's the emissions from burning 1 kilogram of wood. So there's that number. There's somebody else's study. This is what we found when we went out and measured in-use cooking. And the only way we could do it, because it's kind of silly to go knock on people's doors and say, hi, I'm from the United States. I realize you don't really have much to eat, but can I measure your stove? So we went out with NGOs who are working in communities and got these measurements. And there's what we found, factors of 2 to 4 higher than what was measured in the lab. So I'm just going to be showing you examples of how we don't understand these little sources. And usually when we don't understand them, they're higher than we thought. Vehicles. We went to Bangkok, Thailand. And what this is a frequency graph. Here's opacity, which is a measure of particulate emissions, especially black emissions. It's not perfect. Frequency, 100% of the cars measured in the lab were below opacity 60, and 80% were below opacity, say, 25. When you go on the road, and you get cops going out with opacity guns, how many are less than 25%? Less than 10% of the cars. There's such a huge difference between what you can measure in the lab and what is really out there. And why? Because when you have a program to test cars and you say, please come test your car, who's going to show up? The people with clean cars. Wouldn't you do the same thing? Well, I got an old junker. I don't think I'm going in for that. So they're severely undersampled in testing programs. And when we do future projections, let me just show you what happens. This maroon color is super emitters. We don't know much about how they evolve. We don't know much about how many there are, but taking the little information we could get, we put them in a projection of future emissions. And right now, 2010, they look like about half the emissions. This is global. And that is not unthinkable, because you will hear people in this country say 10% of the vehicles produce 50% of the emissions. That's pretty common. But when you project into the future, here come the emission standards. And these colors are different kinds of cars with better and better and better standards. Your emission standards can clean up the normal fleet. Meanwhile, again, we don't know much about this, but meanwhile, according to our best idea of projections, well, the normal vehicle emissions are coming down. That tiny little fraction of the fleet that's smoking is producing a greater and greater fraction of the emissions. So here's a story that says, well, we've got these absorbing particles coming from transport, and we think we can clean it up. Unless you remember that there are these high-emitting vehicles out there, and they behave differently than everything else, and we don't know how many there are. And so in one story, it's getting cleaner. And it may be more like the real story, it's getting worse. Okay, I'm going to skip that bit. So the summary is that there are sectors and fractions of sectors, and by sectors I mean groups like transport and household energy, that have not as much carbon dioxide. So when you think about greenhouse gas policy, you ignore them, but they've got high particle emissions. Those include household solid fuel and high-emitting diesels. And yet, they have significant contributions to climate warming particles and gases, but they're not on the climate change radar. They're not on most people's climate change radar. So small sources matter, especially when you get this kind of poor combustion producing a greater fraction of incomplete combustion. So now these are more questions for you. I'm going to raise some issues. How do we manage climate change now? Climate change isn't just a long-term question anymore. Not when we have Arctic melting. So there's median sea ice in the Arctic. There's what it was in 2007. That's a pretty big change. Here's a dilemma. Back to talking about sulfur. Reducing sulfur emissions is, for the most part, good for health and bad for climate because you're taking off the mask. Some climate tipping points are pretty close. Should we continue with reducing sulfur? Should we save people's lives at the cost of melting the Arctic? That's an extreme way of stating that. What should we do there? Some people have proposed as a partial solution, at the same time, reduce emissions of warming air pollutants like black carbon and also ozone, which I haven't really discussed here. So we've got a group of solutions. The usual one, greenhouse gases building up in the atmosphere. Even if you turn it off, you have the response to today's atmospheric concentrations. And in contrast, just for example, reduce black carbon absorbing particles, they will go away in 2100. They'll be gone in 2100 probably, or 2050 maybe. And you'll be stuck with a bunch of greenhouse gases. But right now, if you turn them off, you turn off the warming immediately. And so if we have this problem where we're close to melting Arctic ice, maybe you want to turn off black carbon emissions now. There are other things that I haven't talked about. For example, when these things settle on snow, you put something black on snow and it melts it more quickly. And so people are now concerned that black carbon is contributing to Arctic melt in addition to just Arctic or atmospheric warming. So we are stuck with this management challenge for greenhouse gases. People are now talking about black carbon as a quick fix contribution to climate solutions, including Hillary Clinton and Al Gore. There's bills in Congress talking about action on black carbon. So Hillary said, look, we have these short-lived climate forcers, black carbon, ozone. Let's deal with them. This is something that's still being floated on Capitol Hill and in places like Arctic Council. Question to you. We have human impacts on climate now. We don't have to wait to see them. We're seeing them now. So how do we balance that? Because we do want to think about the long term. It was failing to think about that long term that got us a bit into this mess in the first place. And yet there are lots of people who say carbon dioxide is the only thing. We have a long-term problem. We have a short-term problem. So that's one question. And then question two is if a single action has both a beneficial result, health, for example, and a negative result, climate, for example, how do we balance those? So again, take home, it's bigger than greenhouse gases. You have lots of pollutants affecting climate. In some cases, especially black carbon and products of incomplete combustion, small sources matter. And finally, there's a portfolio of solutions that includes your standard climate solutions to carbon dioxide and as well includes rapid action. Where, when, what can we do to change this particular location now or soon? So, questions and answers about our fire dilemma. Yes?
I'm just wondering, there are several models that do some computation to predict the temperature increase in the future.
Yes.
And, I think some of the models, they must be, I guess, the impact of the carbon black. So, is it true? But if it's true, then are there any prediction, say, how much contribution from the carbon black to the global warming? Say, I'm saying, say, if we have some prediction, say, 2 or 3 or 5 degree increase, and if we take out carbon black emissions, how much it will impact the temperature increase?
Okay, so the question is, I think, about future temperature change, and you hear scary numbers like 5 degrees C temperature change, C or Fahrenheit. And so the question is, in the future, how much would black carbon contribute to that temperature increase? The statement that you started off with is these models must be considering this. And the fact is that they really aren't, for a couple of reasons. First of all, the projections of how emissions will evolve are really bad. So far, people have just either said it'll go up, sort of linear increase, or it'll come down, they'll be all gone. So there's really no, not yet, a good connection between social and technological behavior that drives these pollutants and predicted increases in the future. So most of what you're seeing when people say give a temperature increase for a certain increase in CO2 is they're really just estimating a total forcing, and they're saying whatever it's from, this is the warming increase. They're not always saying it's this much CO2 and this much sulfate and this much black carbon. In fact, they're usually not. How much of a solution could this be, I think, is a relevant question. If you remove all of the black carbon particles, for example, which we probably could, it would be a small fraction of a solution. But everything is a small fraction of a solution. There was a paper in Nature Geoscience this year, an editorial type of paper, where a group likened it to one of the wedges used by Sokolow, who was an economist who said, you're not going to get all of the carbon solution from one thing. You need little bits, little wedges that make up the entire solution. And they had 15 or 16 different solutions. So the group that wrote this Nature paper said this is about the size of a wedge.
You talked about the atmospheric lifetime of black carbon. Does that allow sufficient transport to get to the ice sheets, if you will? Because what that's discounting is the fact that once it deposits on the surface, it has a lifetime of hundreds of years, I presume, and continued impact there. I don't know enough about global transport, so is your 7-day transport allow it to get to the Greenland ice sheets and the like? And what if you did take into account the fact that it is on the surface?
Okay, so I think there are two questions there. First of all, is the atmospheric lifetime of black carbon long enough for it to get to the Arctic? Yes, no question. You can see it in the Arctic. You can measure it in snow. People are measuring it in snow. It's not all of it getting there, but yeah, some of it is getting there. And then the second question is, once the material settles on the ice and affects the reflectivity of the ice, that's a very strong effect, and it could sit there for a very long time. And the answer there is it really depends on the snow and the ice dynamics. So if it's depositing in the first place, then there's snow. If there's snow, then it gets snowed over the next year, or it could be carried away in runoff. And some of those interactions between the particles and the water, that's the meltwater, are not really well understood. So you could actually have a large lifetime, or you could just have it be carried away. And I think that's one of the big uncertainties in determining the impact.
I also have a two-part question. Is there a relationship, linear or nonlinear, between CO2 emissions and carbon black emission? And second question is that your picture shows that the carbon black is coming from combustion of solid fuels or gaseous fuels. And you know, I mean, everybody probably knows that combustion is a very complicated science. There might be hundreds of free radical reactions involved. So I think even if you have 99.99% efficiency, you still are going to have tons of carbon black emissions into the atmosphere, especially from China. So how can we avoid that if we are still going to burn solid fuels? Because, as I said, the combustion is never 100% efficient.
Okay, so the first question was, is there a linear or nonlinear relationship between CO2 emissions and black carbon emissions? And then the second question was, well, combustion is so complex that even if you have mostly complete combustion, you could still have black carbon emissions. I think you answered your first question with your second. Yes, because combustion is so complex that there isn't a very good relationship between CO2 and black carbon. It's easier just to measure from different kinds of combustion and say, okay, that's what it is for that kind. If you look at the combustion literature and how people try to predict soot formation in very simple flames, it's still very difficult, and so the very complex nature of a real flame, where you have all kinds of turbulence and different temperature pathways, it's just too hard. To answer your second question, I think what you're saying is even if most of the carbon goes to CO2, you could still have some black carbon. And the answer is yes, especially solid fuels. You're always going to form something at the flame front, and that's what you see glowing. Most of the glow is little particles radiating. But those can be burned out. So they have fairly well understood oxidation kinetics. And if you keep it hot enough for long enough, the soot or black carbon that is formed will be burned up. And that's usually how it's done. You don't try never to make any. You just make sure that you burn it before it exits. Nancy.
Two questions.
Everybody's got two questions. This is a pattern here.
Is volcanic eruptions emit a lot of black carbon or not? And then also because forest fires and such are a big emitter, how would you ever be able to control all of that?
Yes, okay. So first question is there black carbon from volcanic eruptions? And the second question is about forest fires. As far as I know, there's very little black carbon from volcanic eruptions. There's a whole lot of sulfate. And you can see the volcanic signal in the temperature record because there will be a dip in temperatures for a year or two following a volcanic eruption. So that says that volcanoes are producing mostly cooling aerosol, if not all. Forest fires, oh dear. There are questions about whether that is controllable and manageable. Certainly a lot of it isn't, especially in very remote locations like Siberia. There's also a lot of question about how much of it is human generated. So some of it is forest management that needs to happen. Some of it is land clearing. Some of it is due to people being there, including a lot of the ones in Siberia, apparently. And so I don't have a good answer for your question. When I think about reducing black carbon emissions, the first thing I do is remove everything but the forest fires and then worry about that later. So you may be right. There may be some that you can't touch. Yes?
Well, sort of follow up on that, I was sort of interested in the natural causes of black carbon. In the historic record, do you see, the caveman here, but do you see periods where prairies would be burned or man-made fires or even natural fires that maybe don't occur as often now? I was curious if that shows up in the sort of, in the modern historic record.
Yeah, yes. And so we're just now getting historic records, like sediment records, with very good time resolution. It used to be that they were like every 10 years, but now there's ice cores that can do seasonal variations. And so you can see forest fires in that. What I haven't seen, because I haven't looked, is how those burning cycles vary. That's something that is really interesting, but I don't know how well that's been characterized. There certainly are people who have looked at not black carbon as an indicator of historic open burning, but the leftover charcoal. So you can see in sediment records when there's more charcoal, that was a higher burning period.
But the intensity is a lot different now than it was in the historic desert fires, depression relating to much larger forest fires. I mean, fires were typically not as expensive, probably also not as hot as they are now. Talking about now being managed like North America.
Yeah, North America would would be interesting. But I don't think there's been fire suppression everywhere. So it would be interesting to contrast those. But again, the place you have to look is in the almost paleoclimate records, the ones that have sort of 100-year or 500-year histories. So that's a topic I don't know very much about. I'm totally curious about the prairies. Yeah. Yes, we have.
We'll take one more question.
We can take ours too.
I had a comment and a question.
Okay.
The comment is, I think this short-term solution is very important because it has a cooling effect. And I went to a seminar not too long ago about the typhoon and hurricane. 1 degree increase in the surface water temperature in ocean will increase 6 inches of rain. That's why there's so much rain in all these typhoon and things. So this short-term, I think this short-term solution is very important. And also, my question is, black carbon contains PAH. How come the lifetime is only days and weeks? I mean, there's PAH in that.
Okay, so the you're thinking of the long lifetime of PAH in the environment, right? When I'm talking about days and weeks, I'm talking about in the atmosphere. So the PAHs aren't orbiting in the atmosphere. They'll be deposited and then maybe re-emitted. But the atmospheric cycle is emission and then washout of some kind or dry deposition. And so the lifetime of black carbon in the environment is actually thousands of years. Arzu.
I remember that geoengineers, they proposed putting some sulfate particle in the stratosphere. So in that way we avoid the whole problem and we have the pollution. So what happens to that idea? And we avoid putting some sulfate particle in the stratosphere.
You're asking me what I think about putting sulfate particles in the stratosphere? It makes me nervous. I think we have done a lot of things with unintended consequences, and I don't think we need to add more of them until we understand the system a little better, if at all. So I'm not convinced that is our first line of defense. There are people who argue that we should understand it just in case we really, really find out that we need to use it. I guess go ahead and understand it, but I would put it far down the list of solutions. I don't think we need to increase our footprint.
Well, we already know what would happen because we reduced sulfate emissions, right? We had acid rain. I mean, we were killing the lakes and killing the forests.
Well, that's the troposphere. So they're talking about putting it in the stratosphere.
So it won't.
So it has a really long lifetime.
It will stay there. It won't come out as gas deposition. Is that? I don't understand.
The chemistry is different, and I'm not sure what the result of that would be.
So we know that having too much sulfate, that there are consequences.
We do indeed.
We kill off the forest because acid rain, we're not in any better shape.
I feel like we're still struggling to understand the chemistry of the troposphere and the stratosphere. Some of it's well understood, and some of it isn't. So I just don't feel like we're ready for a solution like that.
And it doesn't rain up there also.
It doesn't rain, but there is chemistry, some very important chemistry like ozone.